So the next unit that we're going to study, guys, is the unit on equilibrium. And so in this chapter, we're going to study kind of the fundamentals, just the general idea of what it means when something's in chemical equilibrium. We'll also be looking a lot at something called the equilibrium constant, which we will abbreviate KQ. So as I said in class, up till now, we've been looking at reactions, and these reactions, we've always gone, just from reactants to products in one way. But the fact of the matter is that a reaction will go in both directions. So we discussed with the kinetics and the rate laws that the concentration, the higher the concentration, the higher the rate of reaction, because you all have more collisions. So as we go from our reactants over to our products, we're going to use this hydrogen iodine reaction as a model. So as we go from reactants to products, the concentration of my reactants will decrease, and that's shown on the graph right here. And the concentration of my products will increase, which is shown right here. And so over time, what will happen is the forward reaction will get slower, and the reverse reaction gets faster, and eventually they'll get to be the same speed. So once they're the same speed, and the rate of the forward reaction and the rate of the reverse reaction are equal, then these concentrations will no longer change with time. And we have what's called a dynamic equilibrium. And the reason why it's called dynamic is because the forward and reverse reactions are still occurring. So chemistry is still going on, but because they're going at the same rate, the concentrations don't change over time. So if we took measurements, it would look like the reaction stopped. But I want to emphasize once again, because it's going to become important later, that these two processes are still, they're still occurring. Okay, they're still going on. And that's why it's not a static. Things have not stopped. Things are still occurring, and the reactions are going back and forth. So when we look at this equilibrium, we want a way to quantify it. Okay, so you can imagine, I'm going to go back one slide here. So you can imagine that, for some reactions, when this equilibrium gets established, when this rate of forward and the rate of the reverse reaction are the same, we're going to have more product. And then for other reactions, it's not going to form very much product. Maybe these two rates are going to be equal when we have more reactants. And so we want a number, we want a way to kind of quantify and measure what's going to be favored at equilibrium. Will there be more product, or will there be more reactant? And to do that, we use something called the equilibrium constant. So, in general, using our favorite A, B, C, D reaction. So if you imagine a reaction, and the small letters are the stoichiometric coefficients, the big letters stand for the molecules themselves. We'll have A plus B and C plus D. Okay, and so I have my reactants, I have my products, and what I can do is I can define this equilibrium constant. And this is a little bit deceiving as far as the term goes, because it's not like a universal constant like we have in physics. This will be constant for a reaction as long as you don't change the temperature. Okay, if you change the temperature, the equilibrium constant does indeed change. We'll look at how that occurs when you do thermodynamics. But as long as you get the temperature the same, this constant will remain the same. And the way we calculate it is we take the concentration of C molarity. Now we do, remember in kinetics, we didn't use the stoichiometric coefficients, now we do. So this stoichiometric coefficient C becomes my power, and we always put products over reactants. So don't confuse that. Students like to flip this upside down. So it's going to be products. So take the concentration of the product raised to the power of the stoichiometric coefficient, multiply the two together, divide it by the reactants. Okay, and do the same thing. So concentration of my reactants raised to the power of the stoichiometric coefficients. And so for this general reaction, this is how I would write the equilibrium constant. And for the reaction that we just saw back here, between hydrogen and iodine and hydrogen iodide, I would have H2 gas plus I2 gas, going to form equilibrium with 2HI gas. And so I would write this equilibrium constant. I would say, okay, it's going to be the concentration of HI squared divided by the concentration of H2 times the concentration of iodine. Okay, and so this would be how I would write the expression for the equilibrium constant for that reaction. If I were to reverse this reaction, so if I were to say 2HI, and then have what was the reactants, if I have these as the products, we always write the equilibrium constant as written. Okay, so as we've written the reaction. So in this case, I'm going to call this KQ prime, we would say that it's going to be H2I2 divided by HI. So it's going to be the reciprocal of what we had before. So if we reverse the reaction, then we take the reciprocal of the equilibrium constant. If we double all the stoichiometric coefficients for some odd reason, then we would square the equilibrium constant, because essentially I would be multiplying all of these powers by 2. If I cut everything by half, I'd be taking the square root of all of this. Okay, so that's how the equilibrium constant works. And as I said, the most valuable information we get from it is its magnitude. So if we are given an equilibrium constant for a reaction, and that equilibrium constant is greater than 1, notice the products are on top. So if it's greater than 1, then what that means is that when that reaction achieves equilibrium, I'm going to have more products than I will reactants. And vice versa. If it's less than 1, then what that's saying is I'll have more reactants than products, because if it's less than 1, it means this bottom part is greater than the top part. Okay, so that's the value of information. That's what we really use KQ for, is we use the magnitude. It's never negative, by the way. Okay, it's never negative, and we use molarity for it. But if it's greater than 1, we favor products. If it's less than 1, then we favor reactants. Now, one of the cool things that we can do here is not only can we use concentrations, but if we have a gas phase reaction like we do here, there's also an equilibrium constant in terms of partial pressure, so 2HI. And the good news is it works the same way. So we call this the Kp. So this is the KQ in terms of pressure, partial pressure I should say. And you're going to notice as we go through this chapter and the next 2 chapters that we're going to talk about a whole bunch of equilibrium constants, but they are kind of assigned to special reactions, and so we give them different names, but they're all equilibrium constants. So this is the Kp. The one in terms of concentration on this last slide, very often this is called the Kc. Okay, so very often that's called Kc to distinguish it from Kp. So Kp, it works the same way. So I would take the partial pressure of Hi squared divided by the partial pressure of H2 times the partial pressure of I2. So you can express an equilibrium constant in terms of partial pressure or concentration if you happen to have gases. And if you want to transfer between these two, we use this equation. So this is my Kp, this is a Kc. This R, and the derivation of this is in your textbook if you're interested, but it's 0.08206 atmosphere liters per mole Kelvin. That's again assuming your pressure is in atmospheres. T is the temperature in Kelvin. Okay, this delta N can be a little bit confusing. What it is it's the sum of the moles of gas, and only the gas, on products. So on product side, minus the sum of the total moles of gas on reactant side. So in this case that we're seeing here, I would say, okay, well, I have 2 moles of total gas on the product side. I have 2 moles of total gas on the reactant side, so this delta N would be 0, and we would have a situation where Kp is equal to Kc, which will occur if you have the same number of moles of gas on each side. If you don't, however, these two numbers will be a little bit different. And then finally, when we write an equilibrium constant, we have to express in terms of things that could possibly change. And when we have heterogeneous equilibrium, and heterogeneous means that we have, gas or aqueous ions, either one, and we also have a solid or a liquid being used up or forms. So they're not the same phase of matter. So in this case right here, we'd have 2 carbon oxides forming carbon dioxide plus solid carbon, and this will form an equilibrium. Okay. But when we write the KEQ for this, the equilibrium constant for this, we don't put the solid carbon. And I'll explain why in just a sec. So this will be just CO2 divided by CO squared. Again, we square because of the stoichiometric coefficient. Now, why don't we include the carbon? I'm going to use water, and it works the same well, no, I'll just go ahead and use carbon. Okay, carbon has a certain density. Carbon has a certain number of grams per cubic centimeter, and that's a certain number of grams per milliliter, or a certain number of kilograms per liter, or a certain number of moles per liter. And that's the molarity, right? So it doesn't matter how much the solid or liquid you have. The density of it stays the same. And because the density will stay the same no matter what the amount is, the concentration, the number of moles per liter of substance in a solid or gas is the same no matter how much you have. Water, the concentration of water in water, so the moles per liter of water molecules in a sample of water, is about 55 molar. So there's 55 moles per liter of water in water. And it doesn't matter whether you have a thimble full of water, whether you have a bathtub full of water, or an ocean full of water, it's going to be the same concentration. So because the concentration doesn't change as this is reacting, we just don't put it in our equilibrium constant. We just leave it out. So keep that in mind. When we have these reactions, when we have solids or liquids in the reaction, we do not include them in the equilibrium constant. Students always want to do this. They feel bad leaving something out, or I don't know. Don't feel guilty. Go ahead, leave the solids and the liquids out. Okay, so no solids and no liquids in KQ expressions. Okay, so keep that in mind, and then we will do some practice problems during class.